All right, let's solve this problem by coming up with an implementation for the state diagram that's shown below using a one's hot approach. Okay, so let's first consider a flip-flop representing state S0. All right, and we're going to have a clock. And we look at all the ways we can get to state 0. So there's more than one way, so we'll need an OR gate to route the 1 back to this D flip-flop. Okay, so I'm looking at this. Let's make this go green. All right, so to consider S0, I look at all the ways I can get to S0. All right, so I can get there from S2, and I can get there from S1. All right, and then we'll talk about how to get there from itself. All right, so getting there from S2, I have to enable S2 with an input on an AND gate, and then I need to look at the logic that controls when I move from S2 to S0. So you see it's on A bar or B bar. Okay, so that takes care of the S2 situation. Now let's look at S1. Okay, so we'll need an AND gate for that, enabled by state S1. And the logic for that is A C bar. And so we can push that into the same AND function with A C bar. All right, then we have to answer the question of what happens to make S0 return back to the same state, back to S0. All right, so to look at that, we look at all the states that are leaving S0. So you see over here I have this line leaving S0 going to S1. That's on B. So let's mark A, B, and C. And on B, we go from S0 to S1. Right? Another way to leave is on A, B bar. Okay, so A, B bar goes to S2, so the intersection of A and B bar is here. And so that leaves these two squares as the logic that returns S0 back to S0. So we mark that and we see that's these two squares, which would be the logic function A bar, B bar. Okay, so let me move some room. So coming into this OR gate, I need enabled by S0 and then A bar, B bar. Okay, so that takes care of the S0 flip-flop. Okay, now we need to do the same thing for S1. All right, so let me grab this state diagram if I can. And paste it. It's a PDF, so I can't paste that. All right, so let me undo. All right, we'll move everything else down. It's just out of the way. Okay, now let's consider S1. All right, so we need a flip-flop to represent S1. Again, we need a clock. And we need to look at all the ways we can get to S1. Okay, I can get to S1 from S0 on B. I can get to S1 from S2 on A, B, C. I don't remember, this should have been a C variable moving from S1 to S2. Okay, and so then I need to consider what logic takes S1 back to itself. Okay, so we make a little kernel map to consider this. Here's A, B, and C. And we look at all the cases where we leave S1. So notice on C, right here, we leave S1 and go to S2. Okay, and then we leave S1 on A, C bar. Okay, so A, C bar is this region, and from there we go to S0. So that leaves us these two squares for S1. Okay, so the logic for that is A bar, C bar. Okay, so let me move this over and we'll add that in. So we need an AND gate enabled on state S0, and then the logic is A bar, C bar. Okay, so that takes care of the S1 state. All right, so let me grab that, make it smaller, put it out of the way. Now let's consider the last condition where we're looking at S2. Okay, so we'll make a flip-flop representing state S2. And we'll look at the ways that we can get to S2. So I see I can get to S2 from S0 on A, B bar, using this line right here. I can get to S2 from S1 on C. And then I have to worry about how do I get to S2 from itself. And so I look at the logic on that. Okay, from state S2, I look at everything leaving S2. All right, and so you notice here I leave S2 on A bar or B bar. Okay, so marking this Carnot map, here's A, B, and C. All right, so A bar and B bar, A bar is over here, it goes to S0. And B bar is the outer two columns, and we also go to S0. Okay. Then on A, B, the intersection of A, B, and C, we go to S1. So that only leaves us a single square for S2. All right, and the logic for that is A, B, C bar. Okay, so we can finish this problem by moving this over and adding the logic, an enable gate with S2, and then the logic is A, B, C bar. Okay, so that completes the one tot design because we have a flip-flop for each state.